instrumentation laboratory. We call this the MOXIE lab for short. The MOXIE instrument is a demonstration mission designed to prove that we can produce pure oxygen on the surface of Mars. If it's successful, NASA may opt to send a dedicated mission to produce oxygen for humans to use in the future.
So how do we make oxygen on the surface of Mars?
It's actually a fairly easy process. Basically what we do is we take Mars atmosphere, we run it into a unit called a solid oxide electrolysis unit, which is basically a fuel cell in reverse.
Wait a second. Reverse fuel cell? How does that work?
So this is the solid oxide electrolysis unit. What happens is we have Mars atmosphere enter in this line, goes into the SOXY unit. It's then heated up to 800 degrees Celsius. We inject energy into the cathode and anode. And then what happens is oxygen is separated from the CO2 and comes out this line over here. This line here is the waste gases that's left over from the catalyst process.
To test this technology, you're going to need some Martian atmosphere. Where on Earth are you going to find that?
We know the composition of Martian atmosphere. It's 95% CO2 with some trace gases. And there are companies here on Earth that will mix that gas for us. We call it Mars mixed gas, and we use it for most of our testing.
Well, what if we land on top of a mountain or down in a valley? The conditions for extracting oxygen are totally different. We've got to test for all of that.
So the way we test for it is we design an instrumentation system that covers all of the conditions of the instrument. Lower pressures, higher pressures, clogging filters, oxygen purity, all of that stuff.
Why don't we just bring the oxygen with us when we go to Mars?
It's very difficult to bring something from the surface of the Earth to the surface of Mars, and it costs millions and millions of dollars. So it's much easier and better for us if we try to get that resource from the planet.
Well, it's obviously a huge challenge, but we're both really optimistic up here. We're excited to see it on the Mars 2020 mission. Check back soon for some more crazy engineering. Heads up, Watney.
So do you want to do the
Are you ready? Okay.
demonstration?
Yeah.
You want me to record that, or?
Yes.
Okay, well,
I
just
have
bring
a
it towards the,
question.
What's up?
So for the next slides, do you want me to do those? For the food and water ones?
If you want to.
Okay.
Oh, that's right, we have. I forgot about this. We didn't even bring this to the attention. This background that they've all used, Megan designed this. And because we were looking for something special so that we would all have the same background and the same looking presentation. And Megan was tasked with that, and she couldn't find what she was looking for. So she said, screw it, I'll just make my own.
good job.
So,
She quite literally said screw it.
so, and yeah, that's right, so I was looking for Zach's presentation, I'm like, I know I've seen it, and I've had it on my computer before. So we can still do their stuff also. All right, what are we doing first here?
We should probably do the balloon for the lungs.
Okay. So what do we got?
So that balloon is our lungs, and this is just a decompression chamber, which just takes all of the air out of the chamber.
Okay, so you're drawing the air out of the glass chamber here, so we're watching the pressure on the balloon is decreasing. So, go
Yeah,
ahead.
it's expanding as the air is slowly coming out of the chamber. And then as the balloon gets bigger, that's basically our lungs under that low pressure. And it's kind of like when you're going up a mountain or a very high hill and it's harder to breathe because there's less oxygen and there's less pressure. And that's what your lungs are doing under that pressure.
wait for it to come.
We're going for it? No?
Water next.
Okay, so why are you a wimp like that?
I don't like loud noises.
Oh, well, this will be great. Because it won't be loud.
Really?
Do it.
Yeah, yeah.
So this vacuum pump obviously is not the newest vacuum pump on the market. And so what we're able to simulate here is maybe half what Earth's atmosphere is. I don't think we get down to 30% with this thing. And you know, we saw Mars, the pressure on Mars is like 1/100th of what it is. But this is kind of gives us an idea of some of the challenge that we would be up against. And we might as well bring this thing to see if we can stretch that balloon beyond its capacity. But what do you know about noise?
Oh, it like quieter?
It likes what?
So sound needs air or some kind of medium to travel through. And so we've removed a whole bunch of molecules out here, plus this glass is about that thick. So when the balloon does pop, and I'm a big fan of popping the balloons because I really hate balloons. So as evil as I can be to the balloons,
Fair enough.
So big.
there.
Looks like a
Okay, now this will be another fun one, Kylie. We didn't practice this, but we're gonna practice it now.
So you think if your lungs are getting expanding like that, I mean, what does that do to your internal, I mean, everything's getting squished and,
Oh, yeah. Yeah. We didn't do this.
No, I'm.
So right now, we have decreased the pressure quite a bit inside here compared to the pressure that's outside of here. So here, why don't you grab the plate and I'll grab this thing, and we'll see if we can separate it.
my. That's a big
14.7 pounds per square inch on the outside of this thing, so every square inch has 14.7 pounds. Compared with, I mean, even if we got that to 50%, that's a huge amount of weight on the outside of this thing that's not being counterbalanced by the inside of it. And so, and I always, when I do this in my class, I always have the big muscle heads come up and see if they can, and you can't, but as soon as we do this, then I do that, and then, now let's see how hard it is. Oh. So usually I like to have the big muscle heads come up and they can't do it, and then we have some of them.
Why does it remind me of a pressure cooker?
It's kind of, except the opposite.
Okay.
Hey Kylie, what's most of your body made out of?
Water.
Oh,
That's
So-
water.
now you want to see what happens to water when it's under lower pressure. Is that what you're going to show us?
Oh yeah.
This will be fun.
Is it all normal waves?
Oh, we'll find out.
There we go.
So, water has dissolved oxygen, that's how fish breathe, they just pass the water over their gills and they're able to.
Does it have to like?
Nope, it's good. So, when you boil water, you are adding energy to the water molecules, they start to travel faster, the temperature goes up, as the water temperature increases, the ability of that water to contain dissolved gases decreases. So the warmer the water is, the less dissolved oxygen you can have. Well, the warmer the water gets, also the closer you get to something called the vapor pressure, saturation vapor pressure. So when we boil water, when we say that water boils at 100 degrees Celsius, it's because we are changing the vapor pressure of that liquid to equaling atmospheric pressure. And so now that liquid water becomes a gas. It doesn't happen all at once, but it happens gradually. You can see bubbles starting to form in there. So instead of heating the water up and raising that vapor pressure up to the atmospheric pressure, what we're doing called oxygen starts to come out of the water, and eventually we can make this water boil. And that's pretty close. So that's pretty close to boiling. So. Okay, now, we have the water boiling, we're pretty close to boiling. Are you gonna stick your finger in there?
If she doesn't, I will.
I'm not. It's boiling.
It's just,
It was just boiling, don't.
it's just water.
Oh,
It's actually kind of cold.
oh, but it was just boiling.
Boiling.
So one of the things we like to do is threaten to sue the macaroni companies, because they tell you to bring your water to a boil when you cook your noodles, okay? Why are the noodles cooking? They're not cooking because the water is boiling, they're cooking because the water is hot, okay? You can cook noodles in water that's 90 degrees if you can hold the water at 90 degrees Celsius or 200 Fahrenheit or whatever. And so my idea is we could sue the noodle companies because we just brought our water to a boil. That's not gonna do a very good job of cooking your noodles though. And so that's always my get-rich-quick scheme. But
Well, you just do it then.
Well, I
You're
keep
still
forgetting.
teaching. Right.
I keep forgetting to, are we done?
Yeah.
Oh, well, we're just starting to have fun.
Yeah.
Yeah, well, it's another person's
Okay.
turn.
Is this
Megan, you said you would go?
Megan?
I'll do it if you want.
You're a rock star. We should do shaving cream in there.
Somebody forgot the marshmallows.
Sorry.
Oh, yeah, we were gonna do marshmallows. I could go run and see if I have peeps in the room.
Me? Yeah, sure.
I'm gonna read your speaker notes.
I'm gonna sit over here.
Okay. Alrighty, so I am doing food, water, and waste.
Poor Zach. I know you borrowed it.
Alright, so food. Growing plants on Mars is a very difficult task, starting with the soil. The soil on Mars lacks lots of nutrients plants need to grow and produce fruit. So we would probably end up using manure from either plants or agriculture from animals, or from either humans or animals that we'd bring. But this could expose us or the animals that consume the plants to diseases. So having livestock is kind of a big thing. They need lots of space, so that's probably not the most efficient way to get nutrients. And to feed 500 people on Mars, we would need 0.17 square miles of artificial land. The livestock would be kept to a minimum, like chickens and other small animals. And as you can see here, this is a 3D printer that prints food, and we'd probably use this as one of the most efficient ways to, have food. With a 3D printer, the food, the only thing for food we would need would be the dry ingredients and water, and then the process to occur. Many companies have invested into it and have made it clear that it would work on Mars. And an astronaut on the ISS needs is 1.83 pounds of food per meal.
1.83 pounds of food per meal.
Yep.
I
So
saw
is that
a,
2 cups? 2 solid? I mean, would that be equivalent?
what was that?
1.8? I mean, but, cups doesn't go nuts.
Sure, well, it
with weight,
depends on
but-
what you're eating,
Yeah,
I
I know.
suppose, yeah. I watched a program recently, these people have a 3D printer and they 3D print pancakes for their kids. So if their kid wants a porpoise pancake, you can put a picture in, or you can draw a picture of a porpoise on your computer, you can plug it in, and you can 3D print different shapes.
So you add ingredients into the machine.
Pancake mix. It'd be,
It'd be the equivalent of pancake mix, yep, it would be specially formulated with nutrients and stuff. It would be like a slurry kind of,
Okay.
yeah.
We also watched a video in your class about 3D printing meat.
Oh, we did, didn't we?
Yeah.
Yeah, I forgot about that.
And no killing involved, just an animal cell.
Yep, they took an animal cell and they were able to 3D print meat, that's right. That was just this fall, wasn't it?
Yeah, it was like at the beginning of when
Yeah.
we were
I think
doing
it's
the
the beginning of
marshmallow.
second semester.
Yeah.
Well, then
Or
why aren't there
second
people jumping on the bandwagon and making 3D printed restaurants?
It
Wouldn't that be
costs
great?
money.
It probably would be, at this point, it's probably way expensive.
Yeah.
At this point, but
Oh, yeah.
I'm sure in time that the materials that they need to make 3D printers and to actually 3D print stuff will go down over time, so that way it can become more affordable.
Yeah, kind of like, I don't know, what's something that used to be really expensive?
That's right.
They have I was watching that Explain show on Netflix last night, and they were talking about, you know, these massive land animals are basically, I mean, kind of destroying huge amounts of the earth. I don't know the